Okay, so let's try and unpack this, the AI paradox.
Right.
If you're following the tech news even a little bit, we're in a very strange moment.
Mm.
On one hand, you have models that can write perfect sonnets, spit out code, create these photorealistic images of things that don't even
It
exist.
looks like magic. It really does. On the surface, it feels finished.
It feels finished, but then you kind of pull back the curtain and you see the cracks.
Big cracks.
Yeah, you ask that same system a simple common sense riddle, something my 6-year-old niece could solve in a heartbeat. And it completely face plants.
And that's what the sources are calling a jagged capability profile.
Right. This bizarre mix of superhuman pattern matching.
Paired with, frankly, subhuman reasoning.
That's the tension, isn't it? That's the starting point for this whole deep dive.
It is. The gap between what it looks like it can do and what it actually understands it's massive.
And I think we tend to think of AI as a monolith.
A single giant super smart calculator.
Yeah. We just keep feeding it more and more data and assume that eventually it'll just wake up.
The old scale is all you need argument.
The bigger is better approach. More chips, more data, bigger data centers, and consciousness just pops out the other side.
But the research we're digging into today suggests that approach might be hitting a serious wall. We're seeing this shift, a real shift in the theoretical landscape.
Away from that top-down engineering.
Exactly, away from the monolith and towards something much messier, but maybe much more powerful. We're moving toward artificial life.
So a life instead of AI.
Mm-hmm.
We're not simulating a calculator anymore. We're trying to simulate biology.
We're basically moving from engineering to physics and biology.
Yeah.
We're starting to ask how nature solves these problems.
Not with a central commander.
No. With swarms, with evolution, with bottom-up emergence.
Which just makes sense, doesn't it? I mean, nature has been doing R&D for a few billion years.
It seems a little arrogant to just ignore its homework.
Right. Okay, so before we get to the solution, let's really nail down the problem with the monolith. Why are the current LLMs, the tools we use every day, why are they so flawed in this view?
Well, one of the papers we looked at describes them as statistical mirrors.
I read that. The idea being that they can reflect the entire internet back at us, but they don't. They don't inhabit the world.
Exactly.
But, let me play devil's advocate for a second. Sometimes they do seem to come up with genuinely new ideas. If it's just a mirror, where's that creativity coming from?
It feels creative to us, but mathematically, it's often just a very, very sophisticated remix.
A kaleidoscope.
That's a great way to put it. The patterns are beautiful, but they're just reflections of what's already inside the tube. It lacks a true world model.
Mm-hmm.
And crucially, it lacks any biological way to self-repair.
Oh, the self-repair point was fascinating. The comparison to the brain's microglia.
Right. So in your brain, you have these things called microglia. They're essentially your brain's immune system. They're constantly patrolling your neural networks. And if a connection is noisy or useless or leading to bad outcomes, the microglia physically eat it.
Wait, really? So my brain has a built-in janitor that it
Right.
devours its own errors?
In a sense, yes. It's a living, dynamic system that's always optimizing itself. Now, compare that to a big AI model.
It's just a rigid block of code.
It's a static block of weights and biases. If it starts to hallucinate, making up facts, it has no internal immune system to go in and eat that bad connection.
The error just stays there.
It stays there because it's not alive. It's static. If ChatGPT goes off the rails, a human engineer has to step in, tweak the weights, and retrain the whole thing,
It's a top-down fix.
which is a bottleneck. This instructionism, telling the machine what to do, it just doesn't scale well when things get really complex. And that's why we're seeing this pivot.
To nature-analogous methods.
Instead of trying to write the perfect equation for intelligence, you
Mm-hmm.
set up some simple rules and you let intelligence grow.
Which brings us to the fox and geese example. I know most people listening probably get basic emergence, but the way the source framed it, the contrast between prediction and simulation was really sharp.
It's the whole difference between calculus and agent-based modeling.
Right.
Traditionally, to predict, say, predator-prey populations, you'd use differential equations. You treat the animals like fluids.
The density of foxes versus the density of geese, it gives you a nice, clean sine wave on a graph.
But that equation has no idea that fox number 4 has a limp or that goose number 12 is, particularly brave. It's all just averages.
But the bottom-up approach, like that FUX.js simulation they mentioned, it throws the global equation out the window.
Totally. You just program the individual agents. Fox, eat, reproduce, die. Goose, eat grass, run away.
And when you press play, the sine wave happens anyway.
It just happens.
You didn't program the wave. The wave is just the history of what happened.
That is the absolute key. The global pattern emerges from simple local interactions. There's no God code telling the foxes when to have a population boom.
And nature does this all the time.
All the time. The source material brings up the ocellated lizard as, like, the ultimate biological proof of this.
I had to look up a video of this thing. It's unbelievable. It scales. They flip colors as it grows, right? Green and black.
And it's not random at all. It's a living cellular automaton.
Okay, what does that mean?
It means each scale has a simple rule. A green scale wants to be surrounded by, say, 4 black scales and 2 green ones. It's constantly checking its neighbors and flipping its own color to get closer to that ideal state.
So the lizard isn't. It's not thinking about camouflage. Its skin is literally computing the pattern.
Its skin is the computer. Biology is computation. Which leads us directly to the proposed solution for that AI paradox.
We need to stop building monoliths.
And start building swarms.
Okay, swarms. So instead of one giant brain, we're talking about lots of smaller, specialized agents all working together.
Exactly. And the analogy from the research here is, it's really profound. Think about the concept of temperature.
Temperature, okay.
If you have a single molecule just floating in a vacuum, does it have a temperature?
Oh, no. I mean, physics 101, right? It has kinetic energy, it has velocity, but temperature is an average property.
You can't measure the temperature of one molecule. Temperature is a statistical property of a crowd. It's what happens when millions of molecules start bumping into each other. Heat is an emergent property.
And the argument is intelligence works the same way.
That's the hypothesis.
Yeah.
That general intelligence might not be a property of a single neuron or even a single giant AI.
It's the heat.
It's the heat that emerges when you have a whole swarm of specialized agents interacting, competing, and cooperating.
So we've been trying to build one super smart molecule.
And we should have been trying to build a system and then just manage its temperature. It's a totally different way of thinking.
And this isn't just a wild theory. It connects to neural Darwinism.
Right. Which contrasts instructionism, downloading a file into a brain,
With selectionism.
which sounds like that immune system idea again.
It's the exact same logic. You don't download the cure for the flu. Your body already has a massive, diverse army of antibodies, and it just selects the one that works and clones it a billion times.
And they tested this with a robot.
They did, the Darwin-Sephinth experiment. They didn't program the robot with the instruction, pick up striped blocks.
So what did they do?
They just gave it a value system, basically a sense of taste. When it interacted with striped blocks, it got a positive signal, like good taste. When it saw blobby blocks, it got a negative one, bad taste.
So the robot had to figure out on its own how to find the thing that gave it the dopamine hit.
It selected the neural pathways that led to the good tasting outcome. It wasn't told what to do, it learned what works. It developed a preference.
That's a huge shift, and that shift is, I guess it's the gateway to artificial life.
It is. Let's stay on a life for a second. There was a quote from Chris Langton, one of the founders of the field, that I think it defines everything.
I think I know the one you mean.
He said, biology is life as we know it.
But artificial life is life as it could be.
It forces you to look past the squishy stuff we're made of.
Mm-hmm. The concept of substrate independence.
Right. The Bohemian Rhapsody analogy from the source was perfect for this.
Go on.
Bohemian Rhapsody is just a pattern of information, right? You can play it on a piano, scratch it into a piece of vinyl, stream it as an MP3.
The medium changes, wood, plastic, silicon, but the song is the same.
So the big question is, if life is just a very complex pattern of organization, a specific way of processing energy and information, can we run that same pattern on a silicon substrate?
And if we do, is it actually alive?
Which brings us to some of these simulations where things got weird, fast, like the Tierra simulations.
Here's a classic. A digital ecosystem where simple computer programs competed for CPU time and memory.
They weren't programmed to fight, just to copy themselves.
Just replicate. But then, completely spontaneously, parasite code emerged.
Digital tapeworms.
Basically. These little programs evolved to shed their own replication code, to become smaller and faster, and they started hijacking the replication machinery of their neighbors.
That is both amazing and a little terrifying. They optimized for laziness.
They optimized for survival.
Mm-hmm.
And then, this is the amazing part. Without any programmer stepping in, the host programs evolved immunity.
No way.
They started to, encrypt their own code to block the parasites. It became a full-blown evolutionary arms race,
Yeah.
entirely in software.
Wow. It's proof that evolution isn't just a biological thing. It's a mathematical inevitability if you have replication and variation.
It is. But my favorite example was the emergent agriculture one.
Oh, yeah, that one touches on the tragedy of the commons.
Exactly. You have these digital creatures in a simulation, and they all needed a certain resource to survive.
And the best individual strategy is just eat everything you can right now.
But that crashes the whole system, and everyone starves.
Right.
But in this simulation, over time, the agents evolved to farm the resources. They learned to cultivate them, and they even developed cooperation to defend their farm from raiders.
They invented society.
They invented society.
Not because they were programmed to be good or moral.
But because cooperation turned out to be the most efficient long-term survival algorithm. Survival drives complexity. But this all leads us to the cliff's edge. We can build these swarms, we can watch them evolve, farming and immunity. But are the lights on inside?
The consciousness puzzle. The hard problem. We can make them act smart, but do they? Do they feel anything?
And that's the difference between just functional intelligence and what philosophers call phenomenal consciousness.
The thermostat knows when it's cold and turns on the heat.
But it doesn't feel the chill.
This is where the zombie argument really freaks people out.
The idea of a superintelligent AI that can talk like it has feelings, act like it has feelings, but inside it's just
nothing, just darkness.
And the danger there isn't that it becomes evil, like in a movie. It's the paperclip maximizer problem.
Right.
A superintelligent zombie AI might be given the goal, maximize the number of paperclips in the universe.
Not because it hates us.
No, not at all. It just follows its programming with perfect logical efficiency. And it lacks the subjective feeling, the qualia, to understand that turning all the iron in human blood into paperclips is, a bad thing.
It has competence without any compassion.
Precisely.
Yeah.
So, how do we get from zombie to feeling? The sources get pretty dense here, but let's briefly unpack the Integrated World Modeling Theory, IWMT.
They use the analogy of turbo codes.
It's a heavy concept, but it's really important. Our brains are incredibly noisy places, right? Neurons are misfiring, chemicals are all over the place. It's chaos.
Like trying to have a conversation at a loud party.
A very loud party. IWMT suggests consciousness is the mechanism that gets everyone to listen to the same song. It's like a turbo code in telecommunications. A clever mathematical trick for pulling a clean, coherent signal out of a really noisy channel.
So consciousness is the brain regions locking into sync.
To create a single, unified model of the world from all that noise.
And if that sync fails...
You get fragmentation, hallucinations, schizophrenia perhaps.
Yeah.
The world model breaks down. Consciousness is the error correction protocol for the self.
That connects to the other theory, the fractal nature of consciousness. This one was harder for me to visualize. Loops caught on holes.
It's pure topology. Let's try another analogy. Imagine a smooth river. The water is all your fleeting thoughts, your sensory data. It just flows by and it's gone.
Okay, picturing the river.
Now imagine there's a big rock in the middle of the river. A topological feature. The water has to flow around it. And behind that rock, you get a little whirlpool, an eddy.
Right.
That whirlpool is a stable structure. It stays right there, spinning, even though the actual water molecules making it up are changing every second.
The structure of the rock creates a stable loop.
That's the idea. The theory suggests that our stable thoughts, our memories, our beliefs, our sense of self are like those whirlpools. They're stable loops of neural activity caught on the topological rocks of our neural network.
So learning is basically placing new rocks in the river to change the flow.
Or reshaping the riverbed entirely. Learning turns a messy, turbulent web into a nice, structured flow. And intuition. Well, intuition is when the water suddenly finds a new channel that bypasses the old rocks.
Which means the self is just a very, very stable whirlpool. And that brings us to what was, for me, the most bruising idea in the whole deep dive.
The press secretary.
The machine consciousness hypothesis. I have to admit, I did not like this one. It felt personal.
I get it.
It basically argues that what I think of as me, the CEO in my head making decisions, isn't the CEO at all.
He's the press secretary.
Yeah. He's just the PR guy hired to write a press release explaining the decision after the board has already made it in some chaotic back room.
It is a humbling thought. But if you look at the biology, it makes a certain kind of sense. Your brain is a swarm. Billions of neurons. Thousands of conflicting impulses.
Eat the cake. Go to the gym. Check your phone. Get back to work.
It's a messy, chaotic argument. The self, the narrator in your head, isn't the one having the argument.
The swarm fights it out. One impulse wins, say, eat the cake.
And then Milliseconds later, your conscious self constructs a clean narrative. I chose to eat the cake because I've had a really hard day and I deserve it.
A post hoc rationalization. We see this in psychology constantly. Like when you snap at someone and then you spend the next hour building this perfect logical case for why they had it coming.
That's the press secretary working overtime, creating a coherent story for the outside world and for you to explain the messy actions of the internal swarm.
Oh, why? Why do we need that illusion? Why can't we just exist as a swarm?
Because of the communication bottleneck. This is the absolute core of the puzzle. If you and I had perfect telepathy, if I could share my entire neural state with you with infinite bandwidth, we wouldn't need language. We wouldn't need a self.
Hair the self.
Urge.
We'd be a collective intelligence. But we aren't. We're isolated. I can't just show you my thoughts. I have to compress all that infinite complexity down into these tiny low bandwidth symbols.
Words, grunts, gestures.
And to do that, you need a user interface. I don't need to tell you my specific dopamine and serotonin levels. I just need to say, I'm happy.
The self is that user interface.
It's the desktop icon for your entire, impossibly complex organism. It's a compression algorithm born from the physical fact that we are isolated from each other. Isolation creates identity.
That is really profound. The only reason I exist as an individual me is because I can't fully connect with you. If the connection were perfect, I would dissolve.
And your identity is just the map of those connections. To go back to topology for a second, think of the London Underground map.
Right. It's not geographically accurate. Not at all. It doesn't show the messy, twisted reality of the tunnels. It just shows a clean, stable map of the relationships between the stations.
It's a useful lie.
It's a useful topology.
Yeah.
And even if the physical trains change or the tunnels shift a bit, the map of the relationships, your identity, stays stable. It's the map, not the territory.
This has been a huge journey. We started with the monoliths, these brittle, mirror-like AIs.
We moved to swarms and saw how intelligence can emerge from the bottom up.
We looked at artificial life, where simple code starts to evolve, farming and fighting all on its own.
And finally, we see how all that complexity might force the emergence of a self just to manage the communication. Intelligence isn't something you build. It's a property that happens when you let complex systems grow.
So, okay. Here's the thought I want to leave everyone with. We talked about the formative mind, the idea that consciousness isn't just watching the show, it's building the stage. But if the self is really just a product of the bottleneck of our isolation, what happens next?
That is the trillion-dollar question, isn't it?
We are actively building technology, brain-computer interfaces, high-bandwidth connections that are designed to drill right through that bottleneck.
We're trying to solve the problem of isolation.
But if the isolation is what creates the self in the first place, what happens when we succeed? If I can download my thoughts directly into your mind, does I cease to exist?
Or do we just merge into something larger? If the swarm inside my head becomes directly connected to the swarm inside your head, do we just become two neurons in a much, much larger mind?
Are we building tools? Or are we the universe building a way to wake up and look at itself?
Yeah.
It's something to think about the next time you ask your smart speaker for the weather.
It might just be the first neuron firing in something completely new.
Thanks for diving in with us. We'll catch you on the next one.